Hello and welcome to this new episode of Commodore 64 Games Reverse Engineering. I'm going to be reverse engineering a complete game and providing all of the source code so that you can actually use this source code to then create your other games. I'm going to be looking at the shoot 'em up construction kit. So why create all of this new code? Well, to reduce slowdown and flicker in SEUCK games that we used to see before. Remove the sprite to background scroll stop wobble. This is where the sprites kind of slightly disconnect from the background when scrolling starts or stops. And also remove the wasted memory because there is quite a lot of editor code and graphics still mostly present in the final game. This will allow a lot of extra functionality to be added to games because there's full source code and it can be completely customized, for example, by adding extra player weapons upgrades or super weapons, for example, parallax scrolling, enemy homing bullets where enemies can fire at you. Enemy movement AI can be improved rather than just having a pre-recorded attack wave. The title screen can be improved, and also adding functionality like high score tables would be quite possible because there's full source code. In the previous video, we looked at animations and how to find that complicated information which led to this documentation here. Now we are going to look at enemy attack waves. Attack waves in SEUCK is where you can take existing enemy animations and then insert the enemy into a particular place in the level and then record some movement. Inserting this enemy, I can move through the level in rough block jumps first, and then scroll to a fine scroll position where I can then decide where to put this enemy in this particular place in the map, and then it needs to insert the data, which takes a while. There's only 2 units free now, so 2 bytes free in the whole attack waves editor memory. But now going down to test game and choosing proper test. The game starts, the level scrolls into position, and then I should expect to see that green enemy that I just placed down there. So that's the workflow that you would normally go through in the editor. We can use the editor to then reverse engineer this data so we can find out the data format. Here I'm using the editor to delete one of the existing enemies, and we can see that the units free, probably bytes free, has gone up from 2 bytes free to 14 bytes free. Since there is a little bit of free space, I can choose to add another enemy, say for example there. Because there's not very much space available, I'm actually not adding any movement to those enemies apart from maybe tiny little pieces of movement. With more memory available, you can add longer movement or attack wave patterns. There we go, you see there's the other enemy that was just added. So there are 2 parts to the enemy attack waves. The start position, where in the scrolling map where we want the enemy to actually be. Now we can scroll the map in rough block chunks, which is 5 characters high, and then fine scroll, and then we can choose what the animation type is, in other words what the enemy animation type is, and where on the screen the enemy will start moving from, where it is spawned basically, and then after that how the enemy moves. The enemy firing is separate to the enemy attack wave, and also what the score is for the enemy and how it collides with the player. Those are the animation enemy bits, which we haven't looked at yet, and they form part of the object definition. So if I have a look at the enemy and press E, or go and use the menu, there's all of this extra information which is customizable for every single enemy, but we haven't looked at that yet. We want to look at enemy attack waves today. So we can use the editor like before, saving some base data and then gradually changing individual parts of the data to then see how that changes in memory and then to try and understand what the memory layout, what the memory structure is. We do have scrolling portions of the map, and we do have static screens in the map. So this needs consideration, perhaps, although a static screen is just at a certain block position in the level control data. So maybe it doesn't need any kind of special case or anything like that. So let's start with the blank, the SEUCK data, and let's create an enemy, and also let's create an enemy bullet just for this blank data, because we're going to be adding at least one enemy type, probably two, I think. So we want something that's going to be visible on the screen. Moving up to the actual enemy number 1, which is object number 22, I want to select one of the existing sprites in the blank SEUCK editor, and then just put that in as the enemy frame, and I'm going to change the sequence to be 1, like the player, but the enemy is different colored. It's colored white, right? So testing the game, of course, I see the scroll there. I think the scroll is a little bit too fast, but to make it easier to see where we are in the map as well, I'm going to create some extra small blocks to make it obvious when the screen is scrolling, because the enemy placement uses the rough placement first, which is the block level scrolling, right? So I'm just going to create some block variations here just to make the map scroll a little bit more obvious. There we go. So let's scroll down, hopefully to the bottom of the game map, which hopefully will be the first block rows, and then let's just put those there. Make some nice obvious patterns. There we go. So a very simple map, but should be very obvious when it's scrolling. As usual, let's save that as base data. Let's also change the speed of the scroll so it's nice and slow. Make sure that the start of the level is there, and then let's bring in the top of the end of the first level scroll. Let's bring it there so it loops around quicker. Let's save that data. Actually, I think I might save it again the third time round just to make sure I get the right file name, to be honest. One moment, please. Okay, now save the base data again with a blank directory, empty directory. Okay, let's insert our first enemy. This is object number 22, animation number 22, but actual enemy number 1, 0, 1. The rough position, I'm going to set it so that it is 1 block up. Don't forget that each block is 5 by 5 characters, each character being 8 pixels tall or high, so that's 5 times 8, which is 40 pixels tall. The first enemy that I'm adding here is basically in the top left-hand corner of the screen, and then I'm doing that square movement. We can see that the units free goes from 3000 to 2983. I think they put units free rather than bytes free because maybe bytes was a little bit seen as a bit too technical, perhaps. But testing the game, we can see that the enemy goes through its attack wave movement, and then the level loops around, and we get to see that enemy again. Let's save all that data. That's not a very good file name, is it? I think enemy 1 is going to be better. So that is the first incremental change. There's that rough position again. I'm going to be moving, or using the same rough position rather, which is after the first block, and this time I'm putting the enemy in the bottom right hand corner of the screen and just moving it like so. So it's going to move all the way up the screen and then wander over a little bit. The units free has changed again, which is expected. We're adding attack wave data. We want to see that units free decreasing, of course. Now we have 2 enemies that seem to spawn at the same time and then have different attack waves. So let's save that as enemy 2, so we have something to compare against. So the data that I've been changing touches on all of these different types or pieces of data, so that's what we should be expecting to see when we do a binary difference of these all data files. If you've watched my previous videos, this tool, this binary difference tool, should be very familiar by now. There's only 2 bytes changed here. I don't think that that's important. Again, there's only 2 bytes changed there as well. There's a larger sequence of bytes changed there, and then there's a larger sequence of bytes changed there as well. There's a scattering of bytes changed there. I think those individual bytes are also within editor code, or maybe within the game code itself. I don't think they are consequential. Again, those bytes have changed, but it's only a couple of bytes here and there. I don't think that that's relevant to what we're looking for. It seems to be at the start and end of what maybe looks like a data table or something like that at 1DE8. I don't think it's important for us. I think that's important, perhaps. I mean, how many bytes is that? That's 1, 2, 3, 4, 5, 6, 7 bytes all in a row being changed. Maybe that is useful. I don't think those bytes are important. Those bytes at the end are definitely not important. I think that's, looking at the memory address range, it might be character screen data or something like that. This is in the middle of editor code. I can see editor related messages there. Look, copy from sprite number, background, general color, change, rise, fall, wave attack. Yeah, this is all editor code. I think this is probably internal editor data, or maybe some state data or whatever. But look, we've got a whole bunch of zeros there, and then we've got a whole bunch of data that it's changed to in that data block there at 36C something. These ones aren't interesting to me. Those ones that I've highlighted there, I don't think they're important. This is the thing with reverse engineering, is that you need to get a feel for what the data is, how much data that you've changed, and kind of the size of data, and how it would be laid out. You're trying to second guess, or trying to guess what the original programmer would have done. What we can do is that we can, since 2 enemies were added, we can delete the enemies one by one, and then also see what data changes between deleting enemies, right? Because deleting data should also change something in the memory that we can spot. So this is deleting enemy 2 first, in other words, the second enemy that was added, deleting it first, and then without going into the game, although I think it would probably be exercising some game code, right? Because it's doing a scroll and it's displaying sprites and stuff. Without going into the game proper, however, but it's probably running the multiplexer at that point, almost certainly. It allows the first enemy to be deleted, and then we save that data as well. And then let's do some more file data comparison. So let's check after enemy 2 was added, deleting enemy 2, and see what memory has changed. There we go. That's the newer file on the right hand side. I generally put the newer file on the right hand side. That's interesting. So that block of memory again, which was just after that press fire to start message, which is the title screen text. So interestingly, there's that memory chunk which has changed again. But I can see, or rather I did see, 2 FF bytes being added. There we go, there's those 2 FF bytes being added back in again. So it's replacing data that's already been there. So let's do a check between deleting enemy 2 and then 1. So the newer file, deleting enemy 1, is on the right hand side again. That's just a convention that I like to use. Helps my brain think about what data I should be looking for, which is the newest data. And oh look, FF has been or rather FF and 00 has been introduced back into that data again. So that data was added when enemy 1 was added, and then now it's being removed by changing it back to FF again. That's interesting. And then the previous enemy, when enemy 2 was deleted, look, FF is introduced again. Okay, so maybe this chunk of memory just after the title screen text, maybe this chunk of memory contains something to do with enemies that have been placed or deleted, or rather just attack wave data, but it doesn't seem to contain movement data, right? Because the movement data I would expect to take up more bytes. However, what we have here though, look, those 2 bytes there, they have both changed, and they are at the end of the data block. That's interesting. And then those 2 bytes have also changed again when the other enemy was deleted. And that data block seems to mostly contain zeros. Now, if it was free memory in terms of empty memory for empty attack wave data, then I would certainly expect it to be filled with something, right? Apart from bytes maybe at the end of that memory for the attack wave, for the movement data. So let's have a little think about this. What could those bytes signify? So looking at the base file to adding the enemy 1 data, look, you see we've got this long string of updated bytes at the end, but again those 2 other bytes have been changed when the first enemy was added. That is, if it's low byte, high byte data, that is CB3F, so swapping it around, it's 3FCB, and that one there is 1334, which is 3413 in hex, which is also looking like a memory. Now, these 2 memory addresses seem to be at the end of that block of mostly cleared memory. Again, I think this is definitely editor code. Those bytes there, yeah, that looks like editor-related code. I can see it's definitely editor-related code because look in the top right-hand corner there, we've got 2983 units free and then 2965 units free, and insert enemy, delete enemy, menu items. So yeah, so that memory, well, that file offset there, 2B28, seems to be where the start of attack wave data is. So 2B28 in the file offset will be memory address 340C. So I think let's pencil in that memory address as the start of memory that's been changed for attack wave data, and then let's just double check that file offset for the data that's been changed at the end of attack wave data. So 3403 plus 3000 bytes, because we know that 3000 units. Well, look at that. That number there matches almost perfectly with the number of bytes that SEUCK was initially displaying for the number of initially free bytes. Right, so let's just double check that 36E0 should be the end of the file offset of the attack wave data. So 36E0 is moving along to the right. Yeah, it seems to correspond pretty much exactly. I don't think that's a coincidence. I think that pretty much tells us that is the chunk of memory used for attack wave data, because SEUCK is very handily telling us how many bytes are free in the attack wave data chunk, right? And this is data that was introduced to the file. So I think around about there is probably the end of the attack wave data. And look, those bytes, those individual bytes that were changing there, they do look like memory address offsets to these data chunks that are changing in the file in the memory data. So if we translate the file offsets to memory addresses that would have appeared in SEUCK, then they look almost identical. So I think those two memory addresses are keeping track of these two chunks of memory that are being changed. One at the beginning of the chunk of attack wave memory and one at the end of memory inside the attack wave memory. And one, because those two memory address pointers are pointing one at the beginning and one at the end of this block. Yeah, I don't think that's a coincidence at all. I mean, if you have data being added to a large chunk of memory, you need to keep track of, usually you need to keep track of your memory address pointers to know where you've last stored data. Makes sense. You don't want to scan through the entire list of things to find the next free available chunk, for example. It makes a lot more sense to maintain a couple of memory pointers for that. It's a lot quicker. So 341A minus 341C is 7 bytes. So one of the memory address pointers changed by 7 bytes when I added one enemy, and that's increased by 7 bytes. And then this memory pointer, the second memory pointer that was pointing towards the data at the end of the block, decrements by how much, don't know yet, need to calculate that. 3FCB minus 3FC1 is going to be A, right? Yep, in hex, which is 10 in decimal. Maybe the larger chunk of data is to do with movement data. So let's just check those two pointers. That's B this time. So the variation in the second pointer seems to have more bytes when the enemy moves more, perhaps. So we're getting somewhere with this. I think need to edit or need to add more visible data, I think, and to actually copy and paste chunks of data now so that we can actually view them in context side by side. So let's copy those bytes when enemy 1 was added. I don't think the FF is important to the current enemy 1 that was added. I think that that's going to be an end of list markup, right? But we'll copy it just in case. So when enemy 2 was added, we have, the FF was changed to be at the end of that new block of 7 bytes. Deleting the second enemy reintroduces that FF value again. So I definitely think that's an end of list pointer or something. So this is, we can see that the data for the first enemy hasn't actually been changed. See, these bytes are identical to A00CB 3F0C 3800. So the first 7 bytes used for the first enemy, I'm guessing here, those haven't been changed. It's just that the second lot of 7 bytes have been added when the second enemy was added. So this seems to be like a stack of values growing up through memory, right? Looking at these bytes here, look, that seems to be a memory address 3FCB for the first enemy that was added there. So 3FCB, because it's low byte, high byte order, so we swap it around. 3FCB is just before this memory pointer log. So yeah, I think that first memory pointer is definitely at the end of the attack wave data. And then 3FC1 is different to 3FCB. 3FC1 was that memory address for when the second enemy was added. So yeah, I think that kind of tells me that this chunk of memory, these 7 bytes at the beginning, has a memory pointer to the chunk of bytes that was added at the end of the attack wave memory block there. And that FF at the beginning looks like an end of list marker, but maybe these bytes are stored backwards through memory, because when enemy 1 was added, it was adding the memory block right at the end, but enemy 2 added the memory block before the last block of memory. So the end of that attack wave memory seems to be growing down or backwards through memory, whereas the beginning of the attack wave memory seems to be growing up in ascending order, whereas the one at the end is in descending order. Okay, well that makes sense. 2 stacks, one growing from the bottom, one growing from the top, right? So bytes 2 and 3 seems to be the address of movement data, this block here, so it points to the 1, 0, and I think we can get rid of the duplicate bytes now for the first enemy, because we know that's the byte structure, right? The second enemy is pointing at 3FC1. 3FC1 minus 900 plus 1C is 36DD. So 36DD is all of these bytes here that was changed. 36DD is pointing again to that starting 1, 0 value, and then we have FF at the beginning of the block of memory, but I think that that's the end of the list if you're going backwards through memory. Okay, it does look like the top part of that memory is decreasing or descending. So that's interesting to note. So I think we can safely say that bytes 2 and 3 in that 7-byte structure points to the movement data. Not all of the bytes in that 7-byte memory structure have been mapped out yet, so we need to add extra data now. So let's add a sprite, or an enemy animation, right at the beginning of the level. So right at the very, very beginning of the map. No scrolling done whatsoever. Just putting the sprite there in the top left-hand corner of the screen. No movement, nothing at all, just plonking it there. Now when you put the enemy up at the top of the screen for the attack waves editor, it scrolls everything down by 8 pixels, probably because it gives you like headroom to move the enemy up the screen a bit more, so you can actually see where other enemy attack waves are coming in and stuff like that. But that's interesting, right? So this is enemy number 3's data. Now remember, it was at the beginning of the map, so enemy number 3. This is the new data for enemy number 3. Okay, so enemy number 2 and enemy number 1 were put roughly a block up plus a couple of pixels, right? Enemy number 3 is at the beginning of the map. Enemy number 3 and enemy number 2 and enemy number 1 still use enemy object type 1, right, which is object 22, object type 22. Actual enemy 01. Right. Let's create actual enemy 02. Let's by copying enemy number 1 to enemy number 2 slot, but let's change it to red just to make it obvious. I need to add now enemy number 2, which is object 23. Let's just put that 1 pixel up. So the rough position was right down at the bottom of the level, but I nudged it up 1 pixel before placing its start position. I think it was 1 pixel, looked like 1 pixel. Let's save that as enemy number 4, right? Let's have a look at the data for enemy number 4 now and compare it to enemy number 3. And title screen data, blah, 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 blah. Right, so the data for enemy number 3 has not changed, but there has been new data added for enemy number 4, which is kind of what we expect, right? So the first 7 bytes are unchanged, but oh look, I moved the screen up what I thought was 1 pixel, and the value of the first 2 bytes, low byte and high byte order, again, has changed by 1. Now that is interesting. If I push the screen up by 1 pixel row and the value changes by 1, then maybe this is the start scroll position. But also don't forget I changed it from enemy type 1 to enemy type 2, which if you're indexing it by 0, then it's going to be 0 and 1. So let's put enemy type 2, or actual enemy type, actual enemy 2. Let's put the same enemy type, but scrolled up a couple more pixels. Okay, I think that's 2 pixels. Let's just double check that. So there's the enemy type 2. Yeah, that's 2 pixels now. So I've scrolled the red actual enemy 2 pixels, and I've put the same enemy animation in the top left hand corner of the screen again. So let's save that as enemy 5. Right, here we go. So let's check for differences between enemy 4 and 5. Let's get rid of those FF markers. I really do think that FF is an end of list marker. So enemy 5, the 7 bytes growing from the beginning of the attack wave memory. Let's have a look. The newest file should be on the right. Enemy 5 is on the left, but okay, fine, no problem. So yeah, swapping it around, so enemy 5 is on the right, the newest file is on the right, and there are those extra bytes. So enemy 5 is really that data. Okay, maybe I pushed it up more than 1 pixel, but yeah, that seems to be the number of pixels, but maybe I pushed it up by 3 pixels rather than 2. Fair enough, whatever. But yeah, I really do think that is pixel position scrolling up the map, and that last byte didn't change, and I did not change the enemy type, right? So I think that the last byte is the enemy type index starting at 0. So yeah, pixel scroll position, and then these values are changing, but those values are practically identical. All 3 of those enemies were put in the top left-hand corner of the screen, weren't they? Maybe I'm out by a couple of pixels here and there, but I have a feeling that 4 and 5 is going to be positioned. But yeah, we definitely know that byte 6 is the enemy type index. So the last 2 bytes that we really need to figure out are these ones in the file. I'm almost certain that they're going to be position, but we need to test that hypothesis again by inspecting the data. So don't forget, enemy 1 was also in the top left hand corner of the screen, and enemy 2 was in the bottom right. They look like pixel positions, right? Need to test this a little bit more, I think. Let's add some more enemies. We've got values for the top left, so let's do top right, and then let's do bottom right, and then let's do bottom left. These are all with the map scrolling position right at the beginning of the level, saving that data as corners, so we have something to look at. Here we are. The new file is on the right, again by convention. There's a whole bunch of extra data there, which is good. That's what we expect. Let's see if we can decode this. So 1, 2, 3, 4, 5, 6, 7. That's interesting. The enemy that was at scroll position number 3 looks like it's been shifted down in memory, so something has been inserted. Not a surprise. In fact, that's good. So the enemies that were at the beginning of the map scroll have been inserted, which is good. It means that this list, if you like, of structures for the enemy spawn positions is being sorted, or insertion sorted, whatever, with the map scroll position. So that's going to make the code easier for parsing this, because we don't have to parse the entire list, we just have to parse the list for the map scroll position we read. So top right, bottom right, we can see what coordinates have changed. Top right, that looks like, let's get rid of all of the extra data that we don't really need. We'll tidy it up so that it makes it very obvious to see what we are looking at in terms of byte values. We know the rest of the byte values, we just need to clarify on these ones. So we'll copy the byte values from enemy number 1, which was the original enemy, which was top left, right? And then this one is top right. This one is bottom right, and then the last one is bottom left. Now, looking at these, if you assume that they are XY coordinates, right, then these two X values are to the left and to the right, and then the bottom right one, the X coordinate is XA3, which is on the right hand side again. So top left, top right, bottom left. If you assume a left to right, top to bottom coordinate range, then we've got XY coordinates. Pretty obvious by those byte values. From the top left hand corner of the screen, going down and to the right, of course. And it looks like X is divided by 2, which is cool. Now we have enough data for the placement of enemies in the level map, so we can have code to parse that data. We haven't understood fully the movement data, but the spawning of enemies can certainly be parsed. So the first thing to note is that we need to know the total scroll position in terms of pixels for how far the map has scrolled. So the level control routine, which we looked at in one of the previous videos, when we were parsing the levels data all the way back at the beginning almost, this has a notion of blocks and then characters and then fine pixel scrolling there. So when the levels change between static screens and scrolling screens and so on and so forth, we need to recalculate the total scroll position in terms of pixels. And that happens when the next level is set up. It calculates it from the map block position, scroll position, and then the fine scroll position of the screen and stuff like that. So every time the screen scrolls down a pixel, it updates that 16-bit 2-byte counter for the pixel level scroll position. The animation trigger enemies routine is called every frame, and it checks this data, which are these 7-byte data structures that were at the beginning of the attack wave memory structure, which is this memory pointer here. So the attack wave, the current potential attack wave enemy is that next pointer in memory, and then that code will check the pixel level scroll value with what has been calculated from the game scroll, and if it matches, and this is the number of pixel lines from the bottom of the map scrolling upwards, okay, or scrolling downwards depending on your point of view. So it starts at 0, and then the value of 1 is scrolled 1 pixel down. The value of 2 is scrolled 2 pixels down, so on and so forth, right? So when the level scrolls downwards, the counter increases. The 2-byte value in the total scroll position is compared with the intended sprite position in the structure. If it doesn't match, it gets to exit trigger here, and it just increases the total scroll position by how many real movement Y pixels the scroller has done. Okay, so it will either add 0 or 1 in the case of SEUCK games, because the screen scrolls relatively slowly. Once it updates the total scroll position, it then saves back out the working copy of those memory addresses there for the attack wave, for the current potential attack wave enemy in the attack wave data. If both byte values match, then we get to this part in the code where the exact position match, like the comment says, the exact position matches, so this enemy needs to be triggered or spawned. So it uses offset 6, and don't forget that by offset 6 in this structure was the enemy type index, which was 0 based. So it uses the value that's stored in offset 6. It adds enemy type 1, and then it calls the spawn routine, which allocates a free free animation slot for the sprite animations. If there aren't any free slots, it gets to this none free routine, and it just basically skips over the attack wave enemy slot and then considers the next enemy. It continues going through. Because we can have more than one enemy at the same Y scroll position, we need to check them in order and multiple times just to make sure that we cover all the enemies. But if a free animation slot was found, then it basically reads the address for the movement, and it stores that in the animation slot for the enemy's animated movement, which we're not going to get into in this video, I don't think, because this one's quite long, but the next video certainly will. It then takes the address for that, and it has to modify it from what was the SEUCK memory address range to the new code memory address range, right? Because it's a memory pointer, so it needs to do some arithmetic on the memory pointer there to convert that. Then we need to get to the so that's fixing up the memory address pointer that's from SEUCK to the new code. Then after that memory address in the attack wave memory structure is the actual X position and Y position. So this reads the X position while multiplying it by 2 with that ASAdd instruction, and then rotating in the high bit into the high bit for the X position for the sprite, for the animation basically, and then it reads in the Y position from the attack wave memory structure, and then stores that in the animation Y position. So the enemy is basically spawned from the animation block code. We saw how the player animation was spawned or allocated inside the animation routine. This is just using the same function to then basically allocate an enemy. This piece of code here deals with object properties. Now, we haven't gone through the object properties reverse engineering yet, but basically that will be in a later video. But the object properties are tied in with enemy objects in the SEUCK editor. So there are various different things like collisions with the player and the score that you get and stuff like that. So it just basically stores all of that information so that when the enemy animation code runs, the enemy animation code knows how to deal with collisions with the player, for example. So we can enable that code now for triggering enemies. We won't enable the code for enemy firing or anything like that. So let's just assemble and run that code. And what we should see is that we should see the first game, demo game. Here we go. And we have an enemy spawning in the right position in the map. So these enemies don't move because the actual attack wave movement data hasn't been documented yet. That's going to be the next video. But this video shows basically that we can parse and reverse engineer and parse the attack wave start spawning data, if you like, where and what enemy is spawned and at what position on the screen. Yeah, that's the wrong game, isn't it? So on the right is all of the new code. On the left is going to be SEUCK game code, but for the demo game, not the blank one. There we go. So again, by convention, following on from the previous videos, SEUCK code on the left, new code on the right. And we do a side-by-side comparison. So at this scroll position in the map, I'm just using the pause functionality here. We can see the enemy starts getting introduced at the correct place. Of course, on the left in SEUCK, the enemies are shooting bullets and moving around. On the new code so far, the enemies won't move around, but we can certainly see them animate. So scrolling through the memory, scrolling through the game, rather, we can see that the next enemy spawns on the path. We'll pause the SEUCK one on the left until they're roughly in sync. There we go. There's another enemy coming in there. We can see it on the right hand side. And then we should get some static gun placements coming along. There we go. The static gun green enemy looks like it's correctly placed. The other green enemy on the static gun emplacement also looks like it's correct. So there we have it. For this video, that was a successful reverse engineering of the attack wave placement data. The next video, we're going to go into attack wave movement data. And then after that, enemy firing and score and stuff like that, which is probably going to be the enemy bits. So the enemy movement is going to be a little bit of complex data parsing, but hopefully not too bad. So thank you very much for watching these crazy retro games reverse engineering videos. If you like this kind of stuff, then please do consider liking or subscribing to my channel. And if you want to, please add comments, let me know what you think. And also you can request games in the comments section below that I can have a look at. And also if you really like my channel, then you can add a super thanks or a subscription to my channel. Subscribers to the channel, depending on the level, will get things like a Mega Wang 2000 Turbo Edition hardware badge, for example, or early access to my videos. So thank you very much for all of the support for this channel. Take care, have a great day or evening or night, wherever you are.